we'll start the show.
Okay. So, here's our next slide.
Okay.
Thanks, Chuck. Thanks to Chuck. Yeah.
Thank you. Pardon? Oh yes. So those of you that were just in the planetarium, I didn't see it, but thank you, Chuck.
Thanks, Chuck.
I think I've seen almost all the slides. Now our advertising is still a little detached from reality here. We need to. The idea that we're trying to get across is that the meeting starts at 7, and whenever we get to it in the meeting, we will start to talk. It's not a timed event, so it's an event.
So we want everyone here by 7 o'clock. Yeah.
If they want to see the talk, yes.
Yeah.
If they show up at 7:30, they may come in during the talk. So we're first going to hear a couple of brief statements. The first one by Diane, our events coordinator, regarding the upcoming event in June.
Hi everyone, I'm Diane, the event coordinator, and our first event for this year is going to be our annual potluck. Yay! And it's going to be held at Flechman instead of outside at Broder, so that's the one change that we have for this year. But we'll start it at 5 o'clock, and we don't really have to rush out because we're not outside per se. So start planning your recipes, your signature dishes, and plan to mark it on your calendar, and we'll have a great time. Thank you.
Thank you, Diane. Now this potluck takes the place of our June meeting, so we will not be having a meeting in this format in June. And then we're going to touch base with our outreach, the main focus of our club.
Okay. Okay, we had a busy month last month. I don't know, something like 3,000 victims.
Customers.
Yeah. Thanks, Jerry. This month is a little quieter. So really, our next event, we have some schools, but those aren't really like public events. But our next big public event is right here, second Saturday on the 11th, from 8 to 10. Or I think it's 8 to 10, it might be 8:30 to 10. Some of these are starting later. But show up at 8, we'll be there anyway. And, because the museum has a really strict conditional use permit, and we gotta quit by 10. So, especially during the summer, it's tough when you've only got an hour of darkness, or even dark at all. Okay, and then more schools, and then the third Friday is Westmont on the 17th for their public telescope night. Our big outreach event, but it's too late for anybody to sign up now if you haven't already, is Kaleidoscope. Every 2 years, the Girl Scouts camp out at Live Oak out there by Kachuma Lake. And in the past, we've had 2,500 Girl Scouts, and it was like Custer's Last Stand. And what we heard this year was that they're limiting it to 200 people, which really put a kink in the Tri-Counties Girl Scouts because they're like, well, that's maybe one county, but not 3. But they managed to talk county parks into letting, at last count, 800 people come. So it won't be quite Custer's Last Stand, but it'll be up there. And then Tuesday, third Tuesday of the month, Telescope Tuesday, Camino Real Marketplace. We try to make sure we have a moon to look at when we're out there because there's so much light. And then on the 24th, Friday the 24th, it's a star party at Las Flores Ranch Park up by Santa Maria, which is fairly dark. And then our big event, which we'd love to have as many volunteers for as we can, is on Saturday the 25th is International Astronomy Day, and we'll be out at Camino Real Marketplace. From 9 to 4, well 9 for setup, and then 10 to 4 we'll have solar viewing and activities and stuff, and then we'll start to get the moon by about 3 o'clock. And then we're going to break for dinner, and then from 7 to 10 we'll have a star party there. And there's a rank 100 asteroid occultation. I got to put in a plug for asteroid occultation. at 8:40, there's a rank 100, a fairly large asteroid that will going to make a star blink out for a couple of seconds if anybody wants to watch that on video. So that's kind of our plan for this month. Thank you. Oh, there's propaganda over here by the door in those dispensers, star maps, moon maps, webpage listings, that kind of stuff. Thank you.
Literature.
Yeah.
Thank you, Chuck. Okay, well, we're going to go directly to our vice president
Skipping through, I guess.
and a little snappy patter, and then introduce our speaker.
Did he say Saturday Star Party? Did you mention that, Chuck?
Yep.
Oh, you did, okay. We're all there. I'm greeting people. Another fun night. This is going to be good. I'll be honest, as I look out, I didn't think we'd have much of a crowd. It's maybe just members, mostly. We'll find out here in a minute. We got a good guy. I just thought I'd tell you real quickly, because I got a couple other things to say before I introduce our speaker. And I went on to the online to UCLA, and the physics department's all pictured in a row. And the one guy that's smiling at his desk had the word distinguished in quotes next to distinguished professor of astronomy, Dr. Matthew Malkan. And I said, I'll start with him. He'll turn me down. He may not even answer me, but I sent him an email, and he jumped on it. And I heard from him, and he's been back and forth for quite a while. He has a beautiful Asian American wife who may be speaking to us next year, because I believe she's a professor of astronomy down at UCLA as well. So we're the fun club, because it's the fun science. And the speech is, I'm going to paraphrase here, James Webb update. Astronomy revolution begins now. And just in honor of this, we're sending 4 astronauts to the moon. The pink moon, they're on their way. 3 men and a woman. It's interesting. Okay. I assume they wrap themselves into something on the inside that capsule and sleep, but we're not going to go there. It's not that kind of a show. They do have a new toilet, but we're not going to go there either. Some of us in our club wonder how many newcomers flock to our meetings. And this is our regular meeting that we have once a month on the first Friday, but we managed to get some world-class science speakers in here, therefore we decided to invite the public, and that's where I come in by asking right now if you will be so kind as to let me know by raising your hand if you're a first-timer. You've never been here before, you're first.
Okay.
Okay, good. Raise them again because the members want to take you out to dinner later. But not as many. Since they didn't advertise, we've overfilled this place in past meetings, so they dropped all the publicity from the museum. And yet we almost filled the house anyway. Nevertheless, the Astro Hour, that's every Monday. We started it right after getting off the radio. My radio career in this town, I was known as the Baron for many years, ended mid-February 2021, right as the pandemic was coming to a close. That was over 5 years ago. And Jerry and the rest of us who were used to meeting in the studio every other Monday for an hour, talking about astronomy, our favorite subject, decided we got to keep this going, but it can't be on the radio. How do we do it? In fact, we would meet every Friday afternoon or Friday at lunch at a little restaurant, a little cafe along Santa Barbara Street called Judge for Yourself. Was that the name? Yeah. Behind the big building there. Anyway, yes. And so he decided, let's do a Zoom, and the man runs it. Did you want to say something?
The restaurant is no longer there, it changed names or owners.
So that Mexican-American guy that used to service for all those years, he's probably gone, isn't he?
He may be there, but
He may still be.
called something else.
He's the only guy that survived the pandemic without getting anything. But we used to sit there for hours, and we loved it. We came every week. Now, every Monday morning, 11, the SBAU Astro Hour. We just crossed over into our 6th year, and we've done 267 programs, and we talk about everything. You think that astronomy is just confined to the black holes and the stars and that's it. Have you heard of these things? The Penrose diagram? Planets? You know what a planet is? You can imagine, just take the first 3 letters and what does it circle? Interstellar comets, magnetars, parsecs. I'll read about that. That's 3 light years, isn't it? The Great Attractor. And we're now following the Artemis 2 guys out to that pink full moon. So if you do join the club, and we'd love to have you, it's only $20, about the cost of a meal in Santa Barbara these days. You get to meet people and probably make friends with folks like Dr. Sean Kelly, who runs astronomy at City College. Are you here, Sean? He's not here tonight. He normally comes. He's certainly here at the star parties. The heart and soul of our club, if you join, the McPartlands. He's the soul, she's the heart. And we have fun-loving Tessa. Tessa Flanagan used to, she was out, yeah, there's her. She was in the solstice parade and would still be doing it if she could handle it. With the big, you told me it's not the sun you wore. What was that thing on your head?
It was a star with still Polaris.
Did you ever sell it?
No, it's in my garage.
Would you like us to sell it tonight? We started at a couple of She's gonna be in the parade again. Joe Doyle is in the club. Tim Crawford's not here. Jim Hocken, I ran into. Are you here? Jim, okay, you didn't make it, huh? And Diane, of course, with her horse. Anyway, those are just some of the people. Join the club, you're gonna get new friends. Unless you've been like I've been all my life, I don't join anything. It's like those YouTube channels that want you to subscribe and like and thumbs up and stuff I never do. I've always subscribed to the theory, why would I want to be part of a club that would have me as a member? The old Groucho Marx thing. Here are coming attractions, and I'm going to introduce our guest speaker. Next month, May 2nd, Dr. Abigail Freeman, F-R-A-E-M-A-N, JPL, an expert on Mars and the Curiosity rover, and on the rocky inner planets. And she looks like a darling. She's going to be fun. I had to get her by writing her a letter on notebook paper. Because all she posted in YouTube or on Google was an address in Pasadena. It became a moving email address. June potluck follows next month on, that's the Thursday, isn't it, the 12th?
No, it's the Friday.
It is Friday, the 12th. And we're going to set up tables inside.
It's going to be a second Friday or the first Friday?
It's gonna be second Friday.
Okay.
Okay. I thought it wasn't available, we had to pick a Thursday.
Yeah, that's what I thought
that
too.
came up. So, you got time to join and you can bring your favorite casserole too, stuff you made. Dr. Gerardo Aldana, professor of Chicano studies out at UCSB, is an expert on ancient Mayan astronomy in Mexico, and he will be our guest speaker on Friday, July 3rd, 2026. Let the all-new astronomy revolution begin, everybody. Web update featuring Dr. Matthew Malkan of UCLA, distinguished professor of physics and astronomy, and get this, presidentially appointed member of the National Science Board. Dr. Malkan is the principal investigator of the largest observing project undertaken by JWST, the Webb Telescope, in its first year, and is working on plans for the California 30-meter telescope. The man enjoys explaining astronomy to non-expert audiences around the world and in little places like this and on television. And I'm proud to introduce him right now. Ladies and gentlemen, Dr. Matt Malkan, UCLA.
Exuberant person. I mean, you can't say no to him. I got on your webpage, which is very good, and started looking at these. First of all, I figured out finally why it's called the Santa Barbara Astronomical Unit. It took me a while to get the pun. Very clever. Okay. Yeah, that was good. And there's some very good videos on there, and I was looking at, I watched the entire previous talk that you had here, and I looked at some of the other ones too, and I noticed maybe it's just my imagination, but it looked like I must be by far the oldest person who has ever spoken to this group. And so that leads to an obvious conclusion here. I want to make sure that we have something like maybe half of all of our time available for Q&A to hear your questions. Why? Because I feel like I have a lot of personal experiences here. This is not just me talking about some stuff that I read. We're talking about a lot of things here that I lived through. And you might, I mean, nobody else is going to be interested except you might be a little bit interested in that. So let's make sure to have time for that. But, of course, James Webb, so I mean, it's part of my life. I mean, I've seen the telescope at so many stages in its construction, in different places in Maryland and Pasadena and so on. And here it is, this is the final goodbye down in Redondo Beach. And at the time that this was just about ready for launch here, before they folded it up into this unbelievable origami puzzle, people were, everybody was aware of the enormous number of things, let me put it this way, that had to go right, that had to work perfectly. Any one of which, if it didn't work, would have sunk the telescope. So some people might have thought this would be, so many things going right might be almost a little bit miraculous. I don't know. But let's see. Okay, what am I supposed to cover today? Well, I'll try to give you a flavor for what's so unusual about JWST, why it's such a game changer, why it's absolutely revolutionary, why it's already getting astronomers so excited, and then maybe at the end we'll talk a little bit about what might be next for astronomy. JWST is not the end of astronomy, it's not the end of discovery, it's just a gigantic step. Well, let's see, I have several things to tell you why it's a big deal. Well, it's a big deal because it's big. Because it has an enormous mirror, meaning it collects a great deal of light, meaning that it can see much more distant, fainter, further away objects than most any telescope that humans have ever built before. And if you combine this with one other uniquely powerful requirement, it's above the Earth's atmosphere. So that means that you don't have to worry about the twinkling effects that blur out star images. If you look through a telescope now, you'll notice it. In fact, it's very irritating. Astronomy would be so much better off, I have to say, if we didn't have the stupid atmosphere. I often feel that way. Or you can just spend, I don't know, about 100 times more money and launch it into space. Then you don't have to worry about the turbulence, and you can get incredible spatial resolution. The magnification it is phenomenal that you won't really be able to do, even with all of the tricks that you might try with a telescope on the ground. And another bonus here, which really can't be done properly from the ground, is when you get it out there far enough away from the Earth. We really want to be quite a long distance away from the Earth, not this low Earth orbit business. We want to be away from the Earth's heat. We want to get that telescope super cold so that it can sensitively detect not visible light that we're familiar with, that's been studied a great deal. There's real power if you can look to longer wavelengths that are invisible to infrared light. You combine those three, all of these were very expensive and very difficult to do for the first time at this level, then you have a revolution, you have a breakthrough. And, well, all right, I mentioned this already, it was, let's get my pointer. What did I do with that? Because you have a beautiful laser pointer here, it's going to knock your socks off. Oh. So there is the enormous mirror. It had to be folded up. So you have 18 segments here, very thin layer of full coating. And then a big part of the telescope, I don't know if you appreciate how big this is. This is a 5-layer of very thin, basically aluminum slides here, heat shields, which completely shut off the telescope from any heat that might be coming in from the sun or the earth. And this thing is practically the size of a tennis court. Here we don't have a person in it. This here is 23 feet high, but although it's folded up there. So we have this, and this is beautiful. It's just a modern marvel of technology, a triumph of engineering. We have a mirror that collects 7 times more light, has 7 times more area than Hubble Space Telescope, which was our previous greatest telescope, which absolutely, as you know, revolutionized the field for decades with its launch, although the revolution, as you know, started haltingly in jerks and little steps because Hubble keep needing to be repaired and refurbished and so on. Whereas with JWST, as you'll see, everything worked perfectly or beyond the specifications on day 1. So all of the 4 or 5 years it took to Hubble to get up to speed, it's all compressed now almost immediately with JWST. And in spite of the, I mean, I don't know how many people I've talked to said, you know, I think my system is going to fail. There's a few latches that have to snap into place. There's a few cables that have to be deployed, and it's 1,000,000 miles away. There's no astronaut to go up there and fix it. It all has to be done remotely, and we have no second chance. And let's say that they were pretty confident. I have a 99% confidence that my system is going to work. I've asked other people. I'm 99.5% confident, and so on. And after you ask about 300 people, all of whom are 99% confident that their system should work, what are the chances that all 300 simultaneously? You can figure out the number. A lot of us were really scared, and NASA put it all on the line. This would have been, oh my God, the worst catastrophe, I'd say, short of losing a human life, if any of this hadn't worked. Because I'm so fanatical about that, I'm going to take a minute here to actually show you, since nobody was there, when Hubble got in, JW got into its special orbit beyond the moon. It requires a big rocket to get up there so that it can simultaneously be very far away from the Earth, no heat from the Earth, but it can also be in close contact and close proximity to the Earth and never wander away on its own orbit. The moon's gravity helps it find that sweet orbital spot. And let's give a shout out to the Europeans. The European Space Agency heavy launcher, the Ariane, launched it from equatorial South America. Perfect orbit, achieved, put it exactly where it's needed to be, because it's a bit of an unstable location and it needs its fuel to occasionally readjust itself to that point, but it'll be able to maintain its station for decades because the Europeans, bless them, put it in exactly the right starting spot. But anyway, what would be a NASA launch without a video? And I'm going to try to do this with a little spacey celestial music. You'll see all of the steps greatly speeded up. You'll see most of the 300 points, and you'll see all of these delicate little moves. There was no backup for all these. Look at all these single point failures. It didn't happen. Soundtrack, please. It's all folded up. The shroud of the Ariane has been taken off. First, we got to get solar power. Within half an hour, we got to get that. We got to get a communication antenna. Now we're going to start putting out that gigantic sun shield. The lead of that project was actually a former UCLA graduate student of mine. Did a great job. She was scared it wouldn't work. Actually, it did work the first time they tested it. And we saw that. Open up the covers. Now we have to stretch it out. You can't have one tear in that. There's even one little poke look at that, isn't that clever? It has to have a secondary mirror right in front. Comes over the top, it's got to be exactly in the right place. All right, we're 2 weeks in. Finally, we're going to get all of the wings together. This all has to be one perfect parabolic reflecting surface to a fraction of a wavelength of light, which it is. It all has to bring all the light together to one focus, not to multiple foci, as the Hubble telescope famously, unfortunately, did when it was launched. So, no, let's stop it. Everything worked beautifully, and even the PowerPoint is working pretty well. Wouldn't that be funny, though? Little irony there. But we have a lot of astronomers here, and so we're really, the heart of the telescope, aside from the mirror that bringing all that light to a focus and bouncing around, is what are you going to detect it with? All of that equipment, which is really a large, expensive telescope, is right underneath the mirror in this structure here. 4 different instruments optimized to measure different things, mostly about the infrared radiation that JW is picking up. There's a person for scale here. I've used all of these different cameras. They're all complementary to each other, but I'm mainly going to be talking about our big project that uses one of them back there. But it was smart to build forecasts. First of all, they were afraid one of them might break, and it might break at any time, so it's nice to have something else to do science with. But second of all, there's a very clever thought, which was actually borrowed from Hubble, which is all 4 of these cameras are looking up at the focal plane of the focal light from the telescope, but they're looking at slightly different directions. They can all look together. So it's possible to run 2 cameras simultaneously together, both taking data, if you don't mind that one camera is looking at maybe your favorite exoplanet around a star. I have nothing to do with exoplanets. I'm happy that we're looking at them, because then I can take the other camera and look at something, it's about 10 arc minutes, it's a fraction of a degree away. And most people are going, why would you want to spend this very expensive telescope instrument looking at nothing, like just to the side of a star? Why would you waste taxpayer money to that? And I will give you a satisfactory answer in a minute. But let's see. Okay. So now here's where Dr. Shakai comes into the picture. Sorry, Shoko. Sorry, my wife. I don't usually call her doctor. First of all, she produced all of the good-looking parts of this presentation anyway. But more than that, of course, it's very appropriate for her to be here, since JWST and any big telescope, but especially JW, was designed to be a time machine. And you're all probably familiar with that. By the way, because it was designed to look at very distant objects. Occasionally, yes, we can look at some nearby exoplanet, that's wonderful, but really, most of the JWST observing time is looking as far away as it can be, because that's equivalent to looking as far back in time as we possibly can. How many people have watched all of Project Hail Mary? Not enough for this joke to work. So I'm just going to say it. Don't explain the joke to people. They have to go see the movie. All right, I'm about to say the joke here. Boy, we really delivered the heck out of this one. Let's see what Shoko's animation here shows. So there's Hubble sitting here in a low Earth orbit, and it's looking as far back as Hubble can go. It seems fairly far back. And you might, boy, look at all these galaxies in the box there. I wonder if they drew that specially. No, there's nothing special about this. Hubble would see all of these galaxies in any direction that it looks, because they're filling the universe in all directions. It's fairly isotropic on large scales. It's just that Hubble can't see that far back, but still, it was able to achieve something, because when you're looking at a larger distance, you're looking further back in time, and that is of course because counterintuitively, light travels very slowly. It's almost painfully slow compared to the size of our universe. All right, so here's the line. Let me see if I can deliver this properly here. I'm not as nearly as good looking as the person who delivers this movie. Let's see. Okay, class. Who can tell me what's the speed of light? Okay, sorry, I've wanted to do that. I finally have a speed. Of course, the speed of light is 186,000 miles per second, not per hour, but per second. It seems fast around here. There's the Earth. Here's a light beam bouncing around it. Let's count 1 second. 7 times. That is slow. That is painfully slow. But, all right, so let's look back in time, not with Hubble. Let's bring in the JWST, where we can look back so much further that we ought to be able, it was advertised that we ought to be able to look back to the birth of the first galaxies. And so it's a bit like a time machine. It's not exactly like Jurassic Park time machine, right? You can't go there, you can't mess with things, you can't do experiments. I'm not sure you want to do experiments with dinosaurs anyway, but you can look. You can just look, and you can look very carefully. So you're not actually driving a DeLorean back there. You're not messing up history, but you can learn what the universe and whatever was in it. So we can't see the Milky Way, what it was when it was born, but we can see other galaxies that we think might be very similar to the Milky Way as they were born, which probably tells us pretty much what the Milky Way was doing, how it came to be. But we have to account for one very well-known issue here. It's sort of good and it's sort of bad. The universe, as you know, is expanding. I'm not sure if I think it's a good thing or a bad thing. It really has no choice. All right, so who cares what her opinion is about that? In fact, Einstein sort of, as you know, famously messed up his equations in a vain attempt to try to produce a model with gravity that would produce a static, unchanging universe, and of course he made a rather famous failure, went to Southern California, found out, oh my God, I made a stupid mistake, right? His equations really told him the universe should be expanding, and he put in a fudge factor that really was not justified to stop that, and he said it was his greatest blunder of his life, which really is just a big brag about how smart he was. Yeah, many personal blunders, which were much worse than that, but we don't care. I don't know about Einstein. I was just standing outside of the Einstein house in Switzerland like about a month ago. Really, it's more the Einstein condo, really, where he worked out his theory of relativity, working in the Swiss patent office. Quite amazing. All right, but anyway, so Einstein said, I should have trusted the equations. I should have predicted the expanding universe that Hubble was discovering at the same time, unbeknownst to me, in California. Then I could have been really famous. Yeah, total missed opportunity for Einstein. But what does it mean? The photons that we're interested in are from a galaxy that's so far back in time, so far away, that they will be emitted. There's a galaxy, it's why does it look like that? I'll show you what it looks like. They send the photons. In the course of the photons traveling, they go in all directions. One of the directions happens to be to Earth. Thank you. And the universe itself will have expanded, just analogous to an expanding rubber balloon. This doesn't even show how much it might expand. A lot. It's a very stretchy rubber balloon, space-time is. And it will stretch out the photon, which is an electromagnetic wave. So it starts with a relatively high frequency, that means a blue color, but by the time it arrives at the Earth, it may have been enormously stretched out, maybe even into a different part of the spectrum, the infrared part of the spectrum. And we get so much information, we learn so much about stars and galaxies and black holes from visible optical light. That really is what astronomy has specialized in for decades. We've gotten so much mileage out of that, but now we have a new problem. We need to be experts in infrared light, which is much more difficult to take, especially from the ground. And now, the popular take on this, and I'd say some astronomers thought this too, oh, we're looking at that faraway galaxy, it looks redshifted. All of the photons that started out in the visible part of the spectrum have now been redshifted to the infrared. That's just like the Doppler effect, isn't it? You know, the siren is driving away from you, like that. It works for sound waves, it works for light waves. That's really a misrepresentation. Nothing is actually moving anywhere. We're not the most unpopular place in the universe, and everything wanting to get away from us. Space is just expanding, so everything is getting further away from wherever. If there's a Santa Barbara astronomical unit equivalent in that galaxy there, they're measuring the same thing. They're having some existential doubts about whether they're unpopular. They're going to be more unpopular. They couldn't be more popular than SBAU. That was an ad, but that was not really in the talk, but it just came out of it. So why are we actually selling this time machine? How could you get somebody in Congress interested in funding that? Well, here's see if this pitch works for you. I bet it'll work for you. A little bit harder in Congress. We wouldn't be here. In fact, no life would be here. In fact, the universe would be a pointless, uninteresting place unless we had a planet. In fact, we need terrestrial planets, as we learned in the nice planetarium show just a few minutes ago. Well, you can't have a planet without a star. It seems to be leftover debris that is a natural consequence to form if you can form stars. But you can't form a star unless you have a large enough concentration of normal matter to make a galaxy. And since we're interested in our origins, you can't have any chance of understanding our human origins without understanding the birth of galaxies. Okay, I don't know if you buy that or not. I thought it was a reasonable argument. I'll never forget this. Let's see, we were at astronomers like to meet in places. Astronomy is done in a lot of nice places, like Paris, for example. A lot of good astronomers there. I remember we were at this conference, and we started taking bets on, we thought JW would launch earlier than it did. Why did JW take such a long time to launch, which basically multiplied the cost? Now, I'm just going to tell this to you all privately. You don't want to. Because NASA was rightfully just petrified of doing another HST screw-up, initially, screw-up. And so they tested, retested, over-engineered, over-designed, everything over and over again, back foolproof. It was ridiculously over-engineered, and that made the cost, it took longer. That also makes the cost go up. It went up about a factor of 10 cost over what we told Congress it was going to be. And I remember talking to the people who were building this and going, you know, I said, gosh, you can build this huge telescope at like the same price you did Hubble? That's really amazing. They said, yeah, that would be amazing, man. This is the starting price to get us in the door. Once the thing starts, it's going to be very hard for Congress to kill it, which turned out to be Now, I'm not advising doing that again unless you want to try a super collider. It's a risky play, but everything worked out great here. Anyway, back to Paris. At this Paris conference, we were taking bets. How far back will JWST be able to see galaxies? We advertised it would see the first galaxies being born, the first generation of stars forming. Most of the people in that room, I will never forget this, these were the experts, thought, we'll be lucky if we can confirm that a galaxy is actually sending light to our telescope or measuring it correctly confidently when the universe was 8 times smaller than it is today, which is an amazing distance. That's an amazing amount of time back. Basically, you know, about 90% of the way back to the Big Bang, actually. And that was an extrapolation, but that's about what they'd expect. I was the only one in the room saying, I think we can go further than that, you know. Let's let our imagination go a little bit here. So people thought I was a bit, you know, goofy. Maybe it was for some other reason, but probably not. I've heard this before. Anyway, I'm generally a pessimist, actually. You wouldn't know it here. And man, was I so wrong. I'm going to show you some evidence. Well, it's confirmed now that some of these galaxies are sending light to our JWST, which was emitted when the universe was just practically started. It was just 1/20th. That means all the distances, everywhere, distances between any two objects, was 1/20th of what it was now. In fact, when you think about it, okay, this is another problem we have with timescales. You know, speed of light, that was one problem. Human timescales are just so different from astronomical timescales. I'm going to tell you an amazingly short amount of time. These galaxies, some of them I'll be showing to you, were already galaxies. I mean, what I mean by that, it's something when it had turned gas into stars. And the stars are living their lives, producing nuclear fusion power, producing explosions, doing all, maybe making black holes, doing all the really neat things that stars do, only 150 million years after the Big Bang had started. Now, when you consider all of the things that had to happen from a rather uniform, high-temperature, smooth density of material to where gravity had to pull it together into these large inhomogeneities. It started out almost perfectly homogeneous. It's amazing what a short time that was compared to today, 13.7 billion. So, you know, pay attention to the difference between million and billion. It really is a big difference. Actually, at the planetarium show, we were looking at a galaxy, which is very familiar to me. It's called NGC 4594, popularly known as the sombrero. Very well, we study it a lot. It has a nice black hole in the center of it. And someone, the guy who's running the planetarium show, right? Said, well, you know, that's, correctly, that's about 30 million light years away. And everybody said, oh my gosh, this is a galaxy far, far away, you know, looking back to the edge of the universe. That is our next door neighbor. Right? It's 300 million light years. We're talking not about millions of light years, we're talking about billions. And you all know that's a factor of 1,000 difference. And sometimes they don't know that in Washington, but I do. 3 zeros, I understand that. Fine. So, what were we expecting? I don't know what the heck we were expecting, but we have only our detailed knowledge of the universe today, galaxies today, and they're pretty well behaved. I mean, you can always tell what a galaxy is and what is not. I mean, it's a defining concept, a definition of astronomy. Where would biologists be without the concept of a species? They pretty much know what is a species and what's not, or a cell. You know, this is a cell, that's not a cell. It's part of a cell. Anyway, so that we've got this elaborate system based on studying millions of local galaxies here. We have spiral galaxies with these beautiful spiral patterns that are forming new stars as we watch them. Then we have old galaxies which have given up forming any of the stars. They've run out of the raw material to make stars, and it all looks very straightforward. And then you get to the early universe and you don't see any of this at all. Basically, the first galaxies look like little pieces of shrapnel, fragments of things flying around, completely out of equilibrium. Let me just show you some pictures of some of the first galaxies, if you want to call them that. I mean, nothing is settled down here. They're all in the process of assembly into something which will later grow up to be a piece of the Milky Way after it assembles, you know, we need to assemble like 10, 20 of these pieces step by step until we'd actually get to a decent galaxy. I don't mean to put these galaxies down, but that's the way it is. I mean, these are pathetic, really. I'm not even sure I know anymore what a galaxy is, right? I mean, how do you want to define it, actually? They just really defy all of our old definitions. All right, so there's some nice pictures. Now, you're not going to show this at the first press conference to announce to the world the beautiful JWST images. What a disaster that would be. So, we have to look around and came up with, I think, a very good choice of a picture, but it requires a little more explanation and a little more understanding, which fortunately you've already had. There we are there. All right. So this is a spectacular picture of a special target, a special location. We'll see why in a minute. And, okay, they're in the basement there. He knew he was supposed to clap. But there's no way that he actually knew what he was looking at. However, you will be. Let's first look at this. Because it's, I'm sorry, I'm not insulting, right? And that's been done enough. But why this image was chosen and why it's so fascinating and powerful, it's a beautiful demonstration of JWST power, is what I'm about to show you now. It's a little bit complicated, right? I mean, it'll take me a few minutes to explain it to you all. You know, in pretty good shape here mentally. All right. Maybe you're in the same shape. I presume too much. Forget all those comments. Anyway, let's get back to science here. Look at this picture for a minute. First of all, you see enormous concentration of white light from thousands, well, hundreds, thousands of very bright galaxies. They look like the elliptical galaxies I showed you, massive big old galaxies, and they look like it because they are, because they're nearby. It's a famous cluster of galaxies. Actually, all right, can I just make this personal again? This is the cluster by the man who mapped the galaxy clusters of the whole sky, George A. Bell. This is his 2,744th galaxy cluster that he had discovered with photographic plates. Why does that matter to me? First of all, he's an amazing astronomer, and I inherited his office. So I feel, some kind of personal connection. Maybe that's, but anyway, when you look at this picture, the thing, I mean, it's almost brought tears to my eyes. What the heck are all these red streaks? It's covered with red streaks, and they're all making a very distinctive pattern around the center of mass of this galaxy cluster. What the heck is going on? And this is the first time I actually saw it. It's like you're looking in this direction through a distorted glass transparent lens. It's just like, in fact, mathematically, it's very similar to looking at light through the base of a fine wine glass that bends the light and distorts it out into these rings. These are all incredibly distant galaxies, but the light has been remarkably distorted. How could it be distorted? I'll tell you the answer first, then we'll see why. The light has been distorted by the large gravitational attraction of this large cluster of galaxies mass. That's why we wanted to look at one of the most massive nearby clusters we could. That's interesting too. We really want to see what was behind it. And we wanted to see. We do have the world's greatest telescope with a great magnifying power and great sensitivity, and we want more. We want to go even maybe 10, 20, 30 times fainter than if we were just looking at any other random location. And this gravity allows us to do exactly that. It is just amazing. And I remember when this idea was first put into practice, we were actually confirming it. I was a student at Palomar Observatory. We had some nights on the tuners to try to confirm that this is what was happening. This is literally what we were trying to measure here, and I remember very vividly my attitude. It was very much similar, I may say, to Einstein's attitude. Einstein knew about this effect also. It is a spin-off consequence of the fact that general relativity, his beautiful theory, shows that gravity, a large mass, is actually a distortion of space. Actually, really. It alters space in a very specific way. It bends space. And he had an astronomer friend who had literally been bugging him for years to publish a paper. Al, you know, one of the consequences is if you curve space enough, light just travels in what it thinks are straight lines. If you make those straight lines curve together, that's just like a lens. You can make a magnified image of something behind the mass. That's the idea. Now, you had a beautiful lecture about it in February about gravitational lensing. How many people remember that? It's not the same crowd, huh? Okay. So you know already what I'm going to say, and you know for the next 5 minutes, and you can just go to sleep or something. All right, because it was already covered. Okay, so there's one galaxy. This actually is pretty realistic. There's one galaxy back here. The light normally would go out in all directions. A little bit of the light would head towards the Earth, and it would be faint. We'd be struggling to see it. But what good news is, there's such a large mass here. It might be one humongous galaxy. It might be hundreds of galaxies. It actually, space is curved. You can think of it as a rubber surface, you know, and the light just is trying to travel on what it thinks is a straight line. But the straight line takes it towards the Earth from maybe 2 or 3 different directions. So it makes it a lot brighter than it would be because it's a lot bigger than it would be. It's a magnifying glass. Anyway, what a wonderful property. Anyway, Einstein finally publishes things basically just to shut the guy up, stop bugging. And he said in a letter, that's never going to have any practical application, but I just did it to make the guy happy. That's kind of my attitude. I'm not even going to say what decade it was. When I was a punk graduate student, we were a little bit obnoxious, weren't we, Chauffeur? Not you, but I mean, we thought we knew everything. I thought, yeah, okay, there's 2 images of a quasar here. We needed to show that it was actually produced by a massive galaxy. That's when we spent a few nights on the 200-inch telescope. That was the biggest at the time. Very exciting to be using it. And we did manage to prove that, yes, it was gravitationally lensed image of a distant quasar by a foreground galaxy. And I thought, well, thank goodness we proved at least a theoretical possibility actually happens in the universe. Now we're done with this. This is never going to go anywhere. That was a little stunt. You know, they can put it in the book somewhere and so on. This does not have no practical impact whatever on astronomy. And I was kind of right for what, about a decade or 2. But if you stay around long enough, you get to find out all your mistakes. I love that. Look at this, though. This is a zoom in of the previous picture I showed you, that the president was puzzling at. Here, what are we looking at here? This is a zoom in of one red arc. It's all stretched out, but it's actually just one little galaxy. But it's extremely magnified by maybe a factor of 50 times here. It's magnified along an arc here. And you can actually see multiple images. It's reflected here, so this is one view of the galaxy. Here is a mirror image of the galaxy, and this blew my mind. This blew everybody's mind. You see a bunch of little dots here, and you can see multiple images of some of them. There's a dot here, it's the same dot here, here. What are these dots? And some of you have names, stupid names, whatever. By the way, as a former vice president of the International Astronomical Union, I can guarantee you we are not going to give any official name Godzilla to anything. I don't care what they call it in their papers, or how much publicity they want to get. The IAU will not countenance that sort of frivolity. It makes astronomy, well, okay, not fun.
How about Broder?
Oh my God. All right, we need to stop this conversation. These, I can't believe this. these are so magnified, these are actual star clusters forming around this galaxy. You remember star clusters, you probably looked at them at a star party. It looks like a lot of the stars that were first born were born in what's the most ancient star clusters we have now. The Milky Way has a few hundred of these globular star clusters. There's a beautiful one there. Tens of thousands, 100,000 stars, all born together shortly after the Big Bang. And anyway, that seems to be where a lot of stars were originally born. Most of the star clusters have now dissolved, torn apart, but the stars are still here. Maybe we're going around one of them. So that was an amazing discovery, but of course you might be asking more. Matt, those were very pretty pictures. So now I see where the stars are, what shape they're in, and things like that. It was a bit of a surprise, but you know, that's just a bunch of cool images. I'd like to know what's inside. I'd like to know what those proto-galaxies and star clusters are made of. What's inside there? You got anything on that? Oh yeah, it's a harder ask, but of course that's why so much money really was spent on JWST. We want to take that precious light, there's not much of it, and spread it out into different colors, into a rainbow by using a prism. Oh my gosh, then it's really going to be fake. But we have very good instruments to do that, so we'll take the light from one of these mysterious star clusters or galaxies. It's not literally a prism like this, but it's very much, it is pretty much, it's like a prism, it's just different shape. From that, and out the other side comes all of the different wavelengths, which we can then analyze separately. It's called a spectrum. Now, the February lecture told you all about the spectrum. I don't have much to say, except you shouldn't fear this concept. It's not really that bizarre. For example, you could take the spectrum of a neon light bulb, or if you had an arc light of sodium, or let's look at hydrogen. What if you got a tube that just has hydrogen in it? Okay, the long wavelengths, there is light over here. Newton demonstrated that. It's just you can't see it, but you can detect it. Actually, if you put a thermometer here, it'll start warming up. It's infrared radiation. That's where we're going to do the JWST observations. Anyway, just to remind you, if you look at a hot, glowing ball of hydrogen, it gives you this very distinctive, beautiful pattern of bright lines at very specific, uniquely identifiable wavelengths or colors. The strongest one that you can see here is this beautiful hydrogen alpha line. It's pink. That's why basically most of the pictures of gas in the Milky Way are generally going to look pink. They're mostly made of hydrogen. That is the most common element, and it has this beautiful pink emission. It also has a nice sort of blue-green one, and then a number of weaker things in the violet. That's such a distinctive pattern, it's a fingerprint. I like fingerprints, right? So even if I didn't know what the redshift was, I didn't know how far away the photons have traveled, I didn't know how far back in space and time I'm looking, all I have to do is a pattern match. The pattern will be the same. And I can use that then. Firstly, finally, I'll be able to get the third dimension. I'll be able to tell you which are the nearby galaxies, which are the far away galaxies, which are the very far away galaxies, which are the furthest galaxies, which are the record holder galaxies, so close to the beginning of the universe, shortly after Big Bang. I can get all that information. All right, so that sounds like a good thing for the telescope to do, especially designed to do that. We knew that. We had this clever idea. I told you, why don't you let us turn one of the cameras on that has a prism in it. We'll take some pictures, nice photographs to see what galaxies are there. Then we'll run the light through a prism and we'll get the spectrum. We can look for all of those beautiful emission features there. And then we'll begin to tell you what it's made of, right? Because every element has it, and every different physical condition gives you a different fingerprint. So it literally is a crime scene investigation. Okay, secret, my wife would have been a very good crime scene investigator. And I'm not just talking about the kitchen, that was an alternate career. Astronomy is a lot like that, you know, Shoko? we're looking for the clues here, and I just gave you something that's as good as fingerprints to use. And the beauty of this, what I love about this is we run anywhere you look, anywhere you point the telescope, even though it's a small field of view at high magnification, there are tens of thousands of galaxies. So we'll be able to simultaneously measure these beautiful infrared spectra, never been possible to obtain previously, for thousands of galaxies around the sky. Why couldn't we do this somehow from the ground? Too much heat background. You're doing this through a room temperature atmosphere. Your telescope is more or less room temperature, in Hawaii it's more like freezing, whatever. Everything around you is emitting infrared radiation. It's like doing astronomy with all the lights turned on, with your telescope glowing on fire, practically, and you have to remove all of that, and we have struggled. I've struggled so hard to do that from the ground. It really just, you need to get away from all of that, make the telescope as close as you can to absolute zero. That's why all of the tremendous effort in engineering focus on making JW one of the coldest big things, I guess, that we've ever made. All right, and we do this wherever the telescope wants to point. They want to study an exoplanet over there? Okay, we'll look at what the galaxies are over there. They want to look over here? That's nice because, of course, not all directions of the universe are exactly the same. We'd like to get an idea of what, over-dense regions, under-dense regions. They may have had different histories, and indeed they do. I don't know, I have to show you this. Not everybody's going to be into this. My data, okay, we published this data, and everybody's going, Matt, that was real. Let's go back to the Biden picture, right? Now, there is a completely most boring, I would totally ignore that little nothing. I don't know if I call it a galaxy. You spread the light out and see, there's a shorter infrared wavelength, there's a longer infrared wavelength, and you see, oh my gosh, there's a really strong bright line here, very bright line here. I know what that is. That's the hydrogen alpha, except instead of being pink light, it's now infrared light. So I know how far away it is. I know that it's got hydrogen there. But there's more. I was really excited when I saw this. We've got oxygen atoms there emitting. I think you'd have to say that that's pretty highly significant. I'm not making this up, right? That's not just a random error there. So we're actually, what are we seeing here? We're actually seeing that the gas that was surrounding the first generation of stars that formed in a very distant galaxy, and then something else had to happen. Some of those stars, particularly the big massive ones, of which there's always some, they're rare, there's always some of them around, maybe they're more popular in the young universe, they're going to explode as supernovae. The sun won't, sorry, it doesn't do that. But anyway, the supernovae are particularly good in really just a few minutes, even just a few seconds, at running very advanced nuclear fusion reactions that the sun can't do, and producing things like oxygen, magnesium, silicon, sulfur, iron, and so on. All of the heavy elements without which a planet like the Earth, let alone any kind of advanced life, is just unthinkable. So this really is the absolute necessary step for a universe to have life and start thinking about itself, which is what we're doing here. All right. Other experiments that I was very excited about, I'll just show you this one in my own personal taste. I could show you a bunch of exoplanet things, although it's a bunch of spectra where they're trying to see, is there water absorbing the spectrum? It's really a pain. And they're working on it. It's terribly hard. So, and the data look terrible. So I'm not going to show you that. But I do want to show you they are not wasting anybody's time or anybody's money. And they have a lot of tantalizing results already. But let me show you some of my results instead. Whatever. On the best Hubble Space Telescope picture we can take, you can see two galaxies there. They're not that far away. They're obviously colliding, aren't they? They're tearing each other apart with their gravity. We looked at this system over and over again. A lot of the gas has been disturbed by this. It's collapsed under its gravity. It's making a lot of new stars. And a lot of energy being released there, supernovas and so on. So that's, for years, ever since we first started studying this, I thought I knew pretty much everything about that galaxy. There was a lot of energy coming out. We accounted it all for, it's just stars. These are the normal processes that stars go through. They form, they live, they die, they explode. We've seen this, we know it, we've got it all understood, and I was wrong. Ha! The first picture, when you get into the real infrared at high magnification, we've never been able to do so. The first picture, what the heck? All of the energy is coming from like nothing here. There's nowhere over here. There's really almost no other explanation except this is a new quasar. That we had no, it's right in our backyard. I mean, I spent my whole lifetime trying, I guess except for high school, trying to find more quasars at large distances and so on. I can't believe how many of them we missed, which were sitting right in front of our faces. We had no idea of this. And the reason is interstellar dust reddening, and that's why the energy only comes out in the infrared. It was so, and you can see, okay, it doesn't have spikes sticking out of it. That's one thing Star Wars really messed up. All the Star Wars posters, all the stars have diffraction spikes produced by a telescope, which is what you would see when you take a telescopic image or a photograph. The star itself, of course, doesn't have spikes from it. Luke Skywalker should know better. Anyway. All right, so we're finding lots of these. Now, all right, again, I don't want to make it too personal, but hey, we were allowed to first see this data. It was in Pasadena here. We had a team meeting here, and to make it exciting or real, or reality TV or whatever this stuff is called, PBS had a camera crew over there because they were making a NOVA show. Here's a clip from the NOVA show. This is literally at the minute when I saw that first picture there. I guess my jaw is supposed to be dropping here. And they're recording audio too. First of all, before we get to the audio, what's that? I'm the only person in the room with official JWST jewelry. Anyway, I think you still buy these things. All right, so that all automatically makes me a little bit cooler. And I mean, really, I think this is almost a direct quote. Okay. So that didn't get into the, they turned off the audio for that. I can't really put that in a documentary, so just silence, All right, so enough of my stuff. I gotta finish up now. So I said JWST is an enormous leap forward. It's going to keep on producing discovery after discovery at a furious rate, but there's more. Remember, it has such a high magnification that it gives you a very small field of view. Let's try the opposite approach to survey the universe. We want to do it in space, in the infrared, very high magnification. This is basically the Nancy Grace Roman telescope. I actually knew Nancy Grace a little bit. Yeah, see how old I am. I mean, it's Vera Rubin, worked with some of these people, right? And it's great to see them getting the credit that they totally deserve now, including Nancy Roman. The Roman telescope, that's it there. I think it's a JPL, right? This thing is ready to go. It's actually on schedule for this year. It must be launched by next year. Every day that they can speed up the launch, they're about 6 or 7 months ahead of schedule. I know in Japan that wouldn't be a surprise, but in NASA, this is unheard of. Every day that they launch early, they save money on engineers' salaries and so on, which is going to go to the astronomers to do science for the telescopes. All my friends in Pasadena have calendars, clocks. They're literally counting down the days until Roman launches. Why? Because it's specially designed. The back end of this telescope, okay, it has solar shield, cubic fold, and so on. The back end of this telescope has one of the largest cameras ever launched into space. It's humongous. So here's the Hubble field of view, here's the Roman field of view at the same magnification and with at least as much sensitivity as Hubble has, we're going to be surveying the entire darn sky. So, for example, my project, which I'm very proud of, I was bragging on and on about it. Oh, we discovered all these galaxies, thousands of galaxies on the screen. Roman is going to do my project in the first year on millions, tens of millions. Well, how much more do you learn? It seems like you learn a lot more whenever you get thousands of times, tens of thousands of times more information, especially about things that are unusual. Okay, this was sold as a telescope that is going to map out the expansion history of the universe to see how it is decelerated and now accelerated. That might be an interesting question for the Q&A. Anyway, never could be done with JWST. Well, that's great. We don't have the money to launch things into space all the time. Could we make a bigger telescope than the 10-meter telescope that we now use on the top of Mauna Kea? Yes, we can. People haven't been sitting quietly on that. Here's the next plan, the California 30-meter telescope, just to give you an idea. There's the old 200-inch I use. This one I use a lot now. This has made many, many discoveries. The best you can do currently from the surface of our planet. This thing, the mirror, this is just a mirror. The primary mirror is about the size of a baseball in field. And you have to get this into a perfect parabolic shape where nothing can deviate by more than a small fraction of a wavelength of light. You have to maintain it there, and you have to be able to point it anywhere in the sky and track on an object with perfect precision, something that's like 6,000 tons moving around. Sounds like an engineering challenge? It is. Oh my gosh, it's expensive, actually. But look how cool it's going to be when it's actually built. All right. Obviously, it's an animation. We don't have this yet. Looks like it's getting dark. It's time to open this enormous dome. Here it is. It folds out. There's this humongous mirror down there in the middle. Again, it's segmented. See the design? The same idea from Keck telescope that made it manufacturable, doable. Same idea that made JW doable. It's going to make these other giant ground-based telescopes doable. Shoko and I actually were visiting the blanks for these mirrors in Japan. They're all made. They haven't all been polished yet. Some of them have been. I almost got run over by one of them on a paper, which would have set astronomy back. And there, it has to have a laser to try to correct for some of the turbulence in the Earth's atmosphere. Now, Shoko has spent the last 10 years of her career trying to get that laser to make the twinkling go away. She's been studying the giant black hole in the Milky Way, which I also find very interesting. All I can tell you, though, to sum up a long story is, it's really difficult work, isn't it? Yeah. She's not going to argue with that. But, so, we're not standing still on this. The Europeans are in the game, too. We want to build ours in one of the greatest sites in the world, the dormant volcano in Hawaii. The Europeans are already building a giant telescope in the Andes, and they're way ahead of us. This is an outrage, actually. we should have been there now. This is not an animation, this is a freaking picture. This is the mirror cell here. And I'm really worried about that. We had better get some money on our American extremely large telescope projects going right away, so that basically the dominance, the leadership in astronomy, which has absolutely been 100% America for 100 years, since Wilson and Palomar and our big telescopes and so on, all of the discoveries, everything in the last century, totally dominated by Americans. We are on the verge of turning it over to the Europeans. I'm not making that up. I say this in Washington at the National Science Board meeting. So, on a lighter note, I'm hoping that the success of JWST will drive us forward here into the future. We're not resting on our laurels. But I'm surprised how not that many, everybody knows about Hubble. My God, that was the greatest PR since Apollo that NASA ever did. But, our PR has been rather modest. I mean, for example, JWST crochet pillows. What a great idea, but it's not going anywhere. All right, another idea, now you don't know about this, but again, I'm making it real personal. When Shoko and I had a reason to go out to Stockholm a few winters ago, and you might guess what the reason for Stockholm was, if you know about the Galactic Center that Shoko works with, and I was just on as sort of an escort service thing. Anyway, we hung out a little bit with my friend at the University of Stockholm, a very good university. We're working on some stuff with JW together, and I am not making this up. We went to the museum and saw the National Gingerbread House Competition. Seriously, these are the most amazing gingerbread houses you have ever seen. They're in a museum, except this one, which won some kind of prize or consolation prize or something, is a pretty good scale gingerbread mock-up of JWST. And it's still, I checked with Matt, my friend, it's still sitting outside his office in the astronomy department there. It's getting a little bit probably. Let's hope that the real JWST lasts longer. And finally, all right, I was so excited. Yes, we're having our cake and eating too. That's obvious. And we're having our gingerbread and eating it too. Finally, the competition is insane for getting any of your JWST observing proposals approved by anonymous peer review. I was so thrilled, just amazed to win 4 different proposals for the upcoming year. So we're going to show you how many of them were rejected, but it was more than 4. Man, the amount of effort we spent writing all those things. Anyway, obviously I have to celebrate. Yeah. So anyway, that's actually a little bit of a lie there, but anyway. All right, so this is my conclusion. I guarantee you this is true, because every time we've seen this in any science, especially astronomy, astronomy is so much different. Every time you get 100 times, 1,000 times improvement in sensitivity to look at the universe in a new way. Every time, which is what JW is doing now, what Hubble did, what the Roman telescope would do, what the 30-meter telescope would do, what do you find always over and over again are the biggest discoveries? They're always not the ones that we wrote the books about with all the planning documents and the projections and so on. Always the biggest discoveries we had no idea. We couldn't even imagine what they were going to be because we didn't know enough about the universe when observed that closely. And that is certainly going to be true here also. It always is true. I'm done.
Thank you.
Questions from that last talk, they were really the most fun part. So can we do
I
something?
didn't even get to watch that. You,
Oh,
before
it's
I
very
was
good.
here,
It's very good.
2 months ago, he watched the whole recording
I did, yeah.
of, what's his name, Joaquin,
Joaquin, yeah, from UCLA.
Yeah.
Fascinating.
We got a half-hour Q&A, and we're about to do the same. We got the time. The only thing I'm going to ask you is to be saved on the recording, belt it out as loud as you want. I'll let you take the call, the people, raise their
All right,
hands.
so I just pick on
I got my
people.
big question for
All
later.
right, so front row will start for, all right, you next. All right, what's your question, sir?
You didn't have time to mention it, but what do we know about the little red dots that are way in the front?
I mean, that was my next monster discovery I was going to tell you about. The pictures don't look that impressive. I mean, it's what he said. It's a little red
No
dot.
red dots.
Nope. I had no idea these existed. I can't believe we didn't know about these before. What are little red dots? They're some kind of galaxy that's very, very weird, producing a huge amount of energy by a mechanism we don't know. A lot of us think that there's some kind of quasar in the center of it. What do I mean by quasar? I mean a giant black hole that's feeding itself, that has gas fueling itself and releasing the gravitational power in a titanic way. But they're so different from anything anybody's ever looked at before. What I just said is a highly controversial viewpoint. I mean, and they're all over the sky, apparently though, just in the early universe. You know, where did they go? So it's, I'm sorry, I don't have any slides on it. It's a fascinating topic. I could talk on it indefinitely, but you would probably be rather dissatisfied. I'd just be telling you we have only speculations right now. Yeah, they're weird. They're so weird. I said, don't even know whether to classify it as a giant black hole or just a galaxy that's forming a ton of stars in some strange mode that we've never seen before. Any explanation you come up with is going to be weird. Sorry, little red dots. We are so bad at naming stuff. That is, anyway, this is not Godzilla. You had a question.
Is the Roman telescope infrared based also?
Yes, for many of the same reasons. It doesn't have quite as much reach because it's not going to be quite as cold as JW, but it's doing pretty good. And there was a question for you, and then you.
When you were talking about the thumbprints,
Yeah. In the spectrum.
yes, in the spectrum, were you saying that the thumbprints could tell you the age of what you were looking at, or just that different events happen?
Let's see.
Different star events happen in
Interesting.
Good question.
Well, all right, I'm going to go a little bit further than you wanted here. We know how redshifted the light suffered to get here, so we know how long it's been traveling. We now know immediately how far away that galaxy is, so we know how far back in time we're looking. But you didn't even intend to ask this, I bet you. One of the hardest problems in astronomy, okay, so I know when we're looking at it. 500 million years after the Big Bang. I know that. What you really like to know is, where is it in its evolutionary sequence? How long has it been doing this? What was it like before? How old is it? You look at a star like the sun, it is incredibly difficult to know how old it is, because it just sits there pretty much doing the same thing day after day, gradually getting a little bit denser in the core because there's more helium now, because the hydrogen, about half of it is fused. So don't worry, we have a long time here. But this is a problem in a lot of astronomy. I mean, we're not going to hardly see anything happen, in many lifetimes of astronomers. So if you really, I'm sorry to be getting so deep here, but if you really want to know how old something is and how mature it is and where it is in its life cycle and so on, and what are all the events that happened before and after, you have to put together statistical groups of objects and see them in different stages. It's a little bit like walking into a forest where you have all these trees, from little shrubs up to gigantic trees that are falling over and so on and dying. And you have to tell me the life cycle completely of a tree. It's a little bit like crime scene. Maybe not, maybe the chauffeur does this too. And you get to go and take all kinds of data in that forest, measure shrubs, measure redwoods or whatever, and you get to stay there for about 5 seconds. That's it. So you're not actually going to see anything happen, but you might be able to piece together how it evolved if you're clever enough. It's really hard. Sorry, I know that's not what you asked, but I just meant. Sir.
Yes, the red dots again. Do you have any spectral data that might tell us about the composition?
Yeah, they're weird. The spectra have some quasar-like features. The quasar-like features, and that's why I'm putting my money on. There's some very high velocity gas moving around in there. That's a distinctive characteristic of quasars. Why? Because you only get these very high velocities very close to a giant black hole. We're talking about thousands of kilometers per second. Well, that's across the United States in a second. And that would be escape velocity, from a galaxy generally, unless it's in the gravitational field, maybe orbiting around a black hole. You see the same thing at some level in little red dots. That's why I'm putting my money on it. The composition, see, they have heavy elements in there, so they've been through some cycles of supernova, stellar birth and death. So there's other weird things too that I won't bore you with. They seem to have an extremely, like, it's a cocoon. They're like completely wrapped up in a very dense shroud, which I've never seen before. That's why it's so hard to see where the energy is actually originally produced. You cannot have a direct view of it. Classic problem in astronomy, just this one is really on steroids. Sorry, man, I didn't know you were going to do the little red dots thing. That was on my scorecard. Yes.
I was wondering if you think the early galaxies that just look so messy.
Beat up and, yeah.
And, right. How, is it maybe because they have not had time to interact with each other? I'm thinking of the Whirlpool galaxy and its little companion, where they're speculating that the beautiful pylons were created by the companion blasting through the
That's a
sun.
very insightful question, and yes, you're exactly right. You see apparently what's happening on a small scale with some of these little dwarf galaxies now. Some of them are falling into the Milky Way, getting torn apart, and so on. And apparently that was happening big time when galaxies started. Why would that be? Well, for one thing, everything was 10 times closer together in all dimensions, 1,000 times denser, so you'd naturally expect more encounters. But right, these first pieces are maybe just having some of their first encounters, and they're pretty, it looks pretty traumatic to me. I mean, we do find a lot of these things tearing at each other, and so on, and then some pieces get torn off. And yeah, sorry, that's a really waffly answer, but I think you're very much on the right track. You've been waiting for a while.
I'm just curious, I mean, one of the things they observed with these fully formed galaxies, that they're way out in.
That was the opposite surprise from what I was saying. I gotta deal
And I
with
was
it.
wondering if, could we be looking beyond our universe, perhaps into something else? Or do we have to explain how we get a fully formed galaxies producing heavy metals and all the other stuff?
Yeah, all right, I like that. Okay, you've certainly been reading the literature here. I'm gonna get on my Occam's razor, okay? Received something which was an observational surprise, was not really very well predicted by anybody, which I'll tell you what it is in a minute. And I want to go for the most conservative explanation for it. Now, something about, light from objects that, hasn't followed along the history of the Big Bang with the rest of us and so on. I really don't want to embrace that except in the face of overwhelming evidence. We have almost no evidence at all on this. Basically, what you say is true though, even out to moderately large distances. What I mean moderate large distances. Okay, we're looking back to the universe way before the sun was even anybody's idea. Way before the birth of the solar system. Maybe 7-8 billion years ago. So that's way back in time. You can find some examples of galaxies which look old. How do you decide they're old? They don't have any indication of recently formed stars. I spent a huge amount of my research trying to find the recently formed stars because they give me those beautiful hydrogen signals and so on, and we don't find it in these galaxies. So, does that mean our simplistic theories of how galaxies evolve were wrong? Probably they need a little bit of tweaking. My guess on this really is it was very simple to say, okay, a galaxy starts coming together, starts forming stars, forms a lot of stars, and then gradually runs out of gas and it's finished. That is very simple, it's very easy to model mathematically on a computer. I bet that's not realistic at all. You look at these galaxies, they go through generation after generation of rejuvenation. That would not be nice for us too, right? New supplies of gas fall in from outside the galaxy and get it starting all over again. So I think we're just seeing those galaxies in a temporary lull, a phase, and they may get back, just given the right conditions, give them some more food, and I think they may form stars again later. At least that way I wouldn't have to. There's a huge push to grab the biggest headline. So you don't see the biggest headlines. we're pretty much confirming what we thought before. The biggest headline here, and you read it, is the universe is broken. That's a direct quote. Right? You know, all they really meant is that galaxy formation history is more complicated than some of the simplified models we've used so far.
I was actually going to kind of piggyback on that. My question was, is there evidence that points to we are fundamentally missing something, or it sounds like you're leaning towards it's still reconcilable within the models that we study?
All right, if you're talking about galaxy evolution,
Yes.
I'm certainly sure that the universe is not proven to be broken yet. So it's not, it's unbroken until proven otherwise. But part of the reason is that these models, I hate to tell you, are so simplistic. We have a supercomputer. We have a supercomputer now. Yeah, that's great. And they're beautiful to watch. They put in a lot of effects and so on. But the supercomputers, the smallest particles that the most sophisticated simulations have are, I don't know, about 10,000 times the mass of the sun or something. That's a detailed, so it can't really tell you what's really happening inside a galaxy. And the problem is so hard, it may be almost beyond any Earth-sized computer to make a realistic computation of it. So we're being data-driven, as often happens in astronomy. Well, since I am an observer and I get a lot of data, I'm perfectly satisfied with that. Right? I want to look at the theoretical predictions and I like to shoot them down. And according to the theories is left standing at the end, okay, good for it. But we're in that phase right now. We're getting more data to shoot down. There's a lady right behind me.
And so the only astronomy and physics education I ever had is just watching YouTube. And so I just find
it's amazing how much you get. It's scary. I mean, they can put us out of business, frankly.
So my question is, the JWST that was launched to space because of the temperature,
That's right.
Earth's atmosphere, and you get
Yeah.
just spit quality.
Oh my God, you're listening to everything. That's right.
So why is the Chilean and why is the Nancy Grace Roman telescope being built on Earth? Wouldn't it be wiser to just invest in
Oh God, I didn't say this. I'm a freaking idiot. The Roman telescope will be launched into space at great expense because it can only work there. The Chilean telescope and our 30-meter telescope, they're just too big with current technology, although I wouldn't put it past Elon Musk to make it. I mean, the guy has revolutionized. I don't know. So maybe a future generation, they are talking about some bigger telescopes in space, maybe you'd inflate them or something. It's really hard to do. But for right now, we're limited to building a telescope that big with that much light gathering power. I mean, think of how much bigger a baseball infield is than just a 23-foot James Webb Space Telescope. So for certain things, when it's just gathering precious light, these new telescopes will blow everything away. It will be like a whole first time looking. Let me do the back.
Is there any way to piggyback one off the other?
Oh, I love that question. These telescopes are very impressive, but mostly by design, they work in complementary ways. The big, over and over again, it's the combination of these different ways of looking at the same object or the same problems that makes the discoveries, always. All of the Hubble telescope observations, they had a great press office and so on. Those all really became landmarks, advances in our astronomical understanding because what they saw could be followed up from things like the Keck telescope. Without the Keck telescope, I'm sorry to, and other large telescopes, 300-inch, 400-inch telescopes, Hubble wouldn't have had hardly nearly the impact it did. You see the same thing happening again now with JWST. It opens the door. It shows you a new thing. It gets you started. And then you try to do the best you can following it up with every other available resource that you have. And that's really the only way to do astronomy. Again, I'd like to explain that in Washington. That's why we're so expensive. I'm sorry. But, we want to look at the universe in every way that we can if we really want to figure these things out. These problems are too complicated, really, to be completely solved, I'm sorry to say it, by any one telescope. Now, of course, a telescope that has multiple instruments and multiple capabilities, as a multiple threat, that takes you part of the way, but not all the way. You can ask me.
change the topic to Hubble tension.
Oh my God. Shoko, it's your turn.
Okay. What's your position on that in the context of, do you think it is measurement errors, or do you think that with all of the new technology and observations and all the different wavelengths, that we will find something that connects the discrepancies?
I love this. Okay, you know what Hubble tension is? All right. Let me just connect it. All right, you got a minute on this? Okay, it's a minute. The expansion rate of the universe is measured first by Hubble, and another guy that gets no credit, and is a crucial number for all of cosmology, all of astronomy. It tells you the time scale of the universe since the Big Bang. So that was a crucial measurement to make. That's why they called it the Hubble Space Telescope. It was supposed to do it, and it did a very good job of that. And one of the key Hubble findings was published Shakai et al. If it hadn't been for that paper, I never would have met you. You realize that? Anyway, so they thought they had done a pretty darn good job using Cepheid variable stars, which are a standard candle, and then using the rotations of galaxies. The spin tells you how much mass there is there, you see how much light there is, that's a candle, and that still, I believe, is some of the best work that's been done. Some people came along later and said, oh, we can use a special kind of supernova also. So you have all of these classical astronomical measurements of how fast the universe is expanding. Now you have a completely new way of doing it by looking at subtle irregularities in the early universe as revealed in the cosmic microwave background. That's looking back to the universe much further. And you have to do a lot of interpretation of that and understand a lot of things. So they have pushed and pushed and pushed now. And Shoko, actually, you were telling me about a talk that you went to the other day where she heard a new technique, which is using gravitational lensing, and they're trying to measure the Hubble constant, the size scale of the universe, the expansion speed of the universe also. And some of these techniques, if you really believe the precision that they say they're accurate to a few percent. I don't know hardly anything in astronomy accurate to a few percent, except stuff I can measure on the Earth, like the strength of gravity. So it's a big leap, but they say that they disagree with each other. The supernova distances, Shoko's distances and so on, are a bit shorter than the distance scale implied by the cosmic microwave background. Now, that would, if that's true, that would be very serious, because there should be one expansion universe, a uniform universe. It would mean that something pretty basic about cosmology is broken, needs to be fixed. And there's a number of speculations about it. And it's very exciting, by the way, because you can open up new discovery. The greatest thing about a new discovery is all the new questions that you get to ask. Not the answer is the first part of it, right? I don't know. Remember, I told you I'm a pessimist. So a pessimist says there probably isn't any real Hubble tension if those guys would really just understand their uncertainties, meet their errors, bars down, correct for a few systematic artifacts that they just haven't quite gotten it. Maybe they could meet somewhere in the middle. But I have been wrong enough times. I already told you before, I was wrong about the internet, I've been wrong about so many things. Maybe there really is Hubble tension. Shoko, what do you think would be the explanation for these different Hubble constants? That it's expanding at different rates in different parts of the universe? We're in a special part of the universe?
I don't know. I think it's still too early. I am Shoko. I'm not sure about the observation. I don't know who asked the question. I can see.
He's hanging on every word.
But I think I am agree with what Matt just said. I think
got it
it's
from
a
you.
little bit too early to decide which one is correct. There are a lot of systematics. We call it systematics.
What do you want it to be?
Our value was 72, so I want it to be 72.
Oh my goodness. I thought science was supposed to be impersonal and impartial. And we left our emotions completely aside. We don't care who gets the priority. And of course, we're human beings, aren't we, Shakai? Yeah, I'd like it to be 72 also.
See how easy that is?
Those physics fall over there. Yeah, but if both of them are correct, we've got some serious problems, huh? Or some serious opportunities, yeah.
I gotta tell you about this crowd out there, they don't leave, do they? They stick around, they don't even go to the bathroom.
I'm very patiently in back, yeah.
Why is the Roman telescope being designed to be such a wide field telescope? Isn't the point of the telescope to make it more zoomed in?
It has, if you can put enough pixels with enough expensive detectors on there, you can get very high magnification, as JW has, and very large field of view, so you can survey millions of galaxies at a time. That's the plan. They're going in a complementary direction from where JW put all their money in the highest magnification of a small field. It's a different approach. JW cannot do surveys. I mean, I've thought about it. We've been shot down for proposing them. We're not shot down literally, but politely rejected.
So there's just not enough telescope time on JW to take enough pictures to get the full wide angle?
It would take 100 years.
Okay.
or 500 years or something. What was your question, sir?
We talked a lot about things that are far away.
Yeah.
Does JWST have any insight into structures, processes that are closer by in the Milky Way?
Lots. Yeah, we actually saw a little bit about Cassiopeia A at the planetarium show, the supernova explosion. Yeah, anything you look at this closely in a new way with this sensitivity, you find new stuff. I mean, I showed you that hidden unknown quasar in our backyard, just right here, and it's doing that a lot. In fact, it's almost a no-brainer. I mean, take your favorite object that you find interesting and mysterious. Let's have JW look at it. Right? Whatever it is. I mean, I've read and reviewed and rejected hundreds of those proposals, but I do accept some of them, right? If they make a really good case. Actually, if you write a really good NASA proposal, you need to pretty much be able to say that you kind of already know what the solution is that you're going to get, and you need the telescope time and the money just to prove it. I'm not sure, by the way, that all proposals should be like that. What about a blue sky proposal? You know, but if you say, we have, and I've read these proposals too, we have no idea, it's such a cool telescope, we'd like to just go on a fishing expedition. Fishing expedition, that's the worst thing you can say in one of these review rooms. Although maybe we should do a little bit of fishing. I don't know.
So was the cosmic microwave background, is that considered 400,000 years after the Big Bang, and then your JWST is looking back only 150 million years?
Yeah.
Is that what it is? Is it 400,000 versus?
Like JW is sort of, doesn't sound very impressive. Yeah, you're right. So there's this period, yeah, but boy, think how different the universe was. 380,000 years after the Big Bang, we had a sea of hot gas that was nothing but hydrogen and a bit of helium from the first 3 minutes. At very high temperature, it was blindingly bright, like the surface of the sun. No structure almost at all. There were only little overdense regions, a little hotter, a little denser by 1 part in 100,000. Seems ridiculously boring and dull. Thank God, though, some of those overdense regions had a lot of dark matter in them, which had extra gravity, which could slow the expansion of the universe in those regions, slowing it down, making it more overdense, making the gravity stronger, and amplifying in a runaway feedback process to form the first galaxies. But that took quite a long time. It took longer than we could say it, you know. And so I think the microwave background people, they're riding on a high now. I'm very disappointed by the way that the National Science Foundation, just to put some politics in here, it does not seem to be able to put in enough money to the highly recommended, community recommended next generation of microwave background telescopes. To do this properly, if you don't want to go into space, you have to go to the South Pole. Sorry. So it is kind of expensive, but we should do it. Anyway, so then it's amazing how much they've learned, but it still won't tell you how we got here, right? Because the universe that the microwave astronomers study is so ridiculously boring. It's just so, there's nothing almost there at all, you know? And then JW, we're finding the first stars, the first explosions, the first concentrations of gas to make galaxies, and ultimately stars, planets, and people. So they, I mean, neither one would be, could be considered, we have a scientific understanding. It certainly wouldn't be complete without either of those pieces of the puzzle. Cosmic microwave background, as you know, discovered completely by accident. So many astronomy discoveries. Although it is funny how the accidents always happens to people who had worked so hard to make the best instrument. Those Bell Labs engineers had the best receivers, the best antennas of anybody in the world. And when they weren't doing transatlantic communications, they started noticing that their receiver was picking up microwaves from all over the universe and said, what the heck is that?
Dr. Matt, at the risk of triggering the wrath of two of my favorite friends and the most intelligent men in the club who I've asked this to before, I'm going to ask again. I've been waiting for months to find the right speaker. And you touched on it tonight, and I'll try to keep this down. We only got about 10 minutes.
Less.
The balloons you showed early on, showing the small universe at the beginning, what you were just talking about, a couple hundred billion years. Now it's 13.5 billion years, and we're the size of a weather balloon. Okay, that's where the Webb was looking. Where in the world did we point it? Which constellation is where the beginning of the universe resides, if that's what you can call it?
Yeah, where's the center of the universe is what you're asking.
Exactly.
Well,
I didn't want to go that far, but that's part of it.
all right, everybody in this room knows that Ronnie is asking a totally loaded question, right? He's really trying to get me here. I have heard that question so many times, and I think if we just lived in a sort of a basic, three-dimensional universe, well, I still don't think that question could be answered. Basically, it's really, really, really infinite.
They pointed it somewhere. Where did they point?
It doesn't matter where the first order, wherever you point it, you're going to see the same, roughly
Really?
the same
Turn
thing.
it around 180 degrees, you'd also
It's the
go
same
back
thing.
13.5 billion years.
You got it.
So somehow
That's right.
that little smaller universe size of a grapefruit
Mhm.
is now like the onion. It's a layer of onion on the outside. But that's the present out there.
I'm sorry to burden you with this, but I mean, it goes back to the microwave background and all that. When the universe was a billion of a second old, it apparently went through a horrific expansion. I know it's expanding now. I'm talking about an exponential expansion where it suddenly, as you said, the region that we can see now went from something smaller than an atomic particle to something about the size of a grapefruit. And it's been expanded and it's went back to its normal expansion. That's called inflation. Now, one of the immediate implications of this theory, which is very well supported by theory and by a lot of observations now, including the microwave background, is that we are now living, everything we can see out to the farthest distance, 13.7 billion years back. That's a certain finite distance away. It's our horizon. We can't see, at the moment, past that, and eventually we're going to be able to see that if the universe keeps accelerating like it appears to be doing. But at the early stages of the universe, there must have been, we're just looking at the most minuscule, tiny, teensy fraction of a much larger universe that we will never be able to see anymore. That is what inflation says. And in other words, the part of the universe that we can't see is probably 10 to the 90. That is 1 followed by 90 zeros larger than everything that we can see now. And if you don't think that's close to infinity, to me, that's pretty darn close to an infinite universe. Now, an infinite universe does not have a center.
Yeah.
Sorry. It is really, most humans are not comfortable with that. I'm not comfortable with that, saying it, but I don't know what else to tell you.
We are about ready to vacate, but listen, I have some gifts for you on behalf of the club. I'm gonna give them to you along with your incredible drive up here gas check. That's our official cup.
Oh, I love this. I love this.
Here is our official hard to sell kit.
I'm gonna go around.
And then our treasurer threw in an extra prize because you have come the closest to looking like Mr. Rogers than anyone. I know that. That's why you did so good.